Okay, today we will consider first of all sheaves and the relation to sheaves, and our aim is to prove that first of all, the set of open sets is determined by sub-sheaves of a constant sheaf or terminal sheaf. And also we want to understand why every sheaf on a topological space can be regarded as a sheaf of cross sections of some bundle. Okay, sheaves. Oh no! Oh no! Oh. Okay, sheaves and sheaves. I recall the definition of a sheaf. We on a topological space. Open set U determines a press sheaf home and for all open set for each open set V, we can define this home as follows. It equals 1 if V is subset of U, and empty set otherwise. And 1 is a one point set. Is 1 point set, and it is called this press sheaf is called a representable press sheaf. And so we will write y of u for this object. Okay, and definition. Sheaf on U in the category of open set of all open sets is defined to be a subfunctor of y of u. Okay, and we may think also about this object as a subset, subset S of open sets on U, such that if V0 is a subset of V, which belongs to S, it implies that V0 belongs to S. And each indexed family vi in U generates a sieve S on U in the following way. The set S consists just of all sets, of all those open sets V with this condition for some I. In particular, we may consider some covering, and we may consider corresponding sieve, and we will say that this sieve is covering sieve. Okay. And proposition. A press sheaf P on a space X is a sheaf if and only if for all open set, for any open set U of X and every covering sieve S on U, the inclusion S into Y of U, inclusion of functors induces an isomorphism. This isomorphism. Okay, let's prove this. Construct the equalizer in the category of press sheaves. E is an equalizer. We consider some covering of the set U and the corresponding equalizer. E consists of those families of elements those families of elements xi in P ui such that xi restricted to ui intersects uj equals xj restricted for all I and j. Okay, and now by means of sieve, we can replace these coordinate notations, and we can use free coordinate notations, and it gives sieve. Replace current UI by corresponding sieve. S. I recall that it consists of such sets V with V is a subset of some UI for some I. We consider all of this set V, and for each V, we can define X V to be Xi restricted to V. This is independent of the choice of the index with the property with a subset of I. And then equalizer can be described as a set of those families of elements xv. Okay, and we have that xv restricted to v prime equals x v prime whenever v prime is subset of v. Now we can think about S as a functor regard S as a functor from open sets to the sets such that S over V equals 1 is a one point set if and only if V belongs to S where S is a set, and S over V is just empty set otherwise. Okay. Each element xv from PV. PV is a set of functions of the open set V. This element is just a map SV to PV, and if V belongs to S, then we have that SV equals 1, and we have that this one maps to XY, XV, and otherwise empty set maps to XV. That is just an empty element. Just perhaps so. Okay, and we can think about equalizer as just a set of natural transformations. Natural transformations between two functors, S and P, because we have because we think about any element as a map for each V. Okay, as this natural transformation such that theta of 1 equals xv. And then we can form the following diagram. We know that E is equalizer and is just a set of natural transformations. Then we can write that it is a home between S and P, and in this equalizer. But also we have we have a PU, and we want the fact that P is a sheaf. That is PU is also equalizer of this diagram, and hence we should have an isomorphism between these objects. But IS induces the following morphism between this home and this home. IS is the map between S and Y of U. It is just inclusion in some sense, and we have isomorphism here. It's just a Yoneda isomorphism. And thus we should have that these objects are isomorphic, and hence these homes must be isomorphic if we want to obtain that this object is a equalizer too. Okay, thus the condition that PU is a equalizer it is the same as a statement that we have a isomorphism. Okay. And now I want to formulate the following proposition. Which tells us that for all space, the category of sheaves has all limits and also the inclusion of sheaves in press sheaves create these limits. Creates these limits. Sorry. of course, we have the following obvious inclusion: sheaf on X in sheaves on X. And it turns out that limits in limits in press sheaves generate limits in sheaves in some sense. We can prove this directly, but there is another way, and we will discuss about this way later. The direct proof. It's quite easy. We should prove it is sufficient to prove that we have all equalizers. Prove that we have equalizers. Form an equalizer in the category of press sheaves, and prove that where of course F and G are sheaves in the category of press sheaves. Then let's construct pullbacks point-wise. What does it mean? If we have functors press sheaves X, Y, and B, then we can form a pullback pointwise. It means that is a following object. This is just a limit is a category of set of the following diagrams. Where F and G are natural transformations. Okay, and it is known that a home functor preserves limits. And hence we can form the following diagram. We take this functor we consider this equalizer and take the functor, the home functor, and then we obtain the following. But if P equals the representable functor y of u, then we obtain the following. Equalizer it will be also equalizer because of this observation. Okay, and we also have the following isomorphisms. We know that it is isomorphic to home from S to F, and it is isomorphic also to home from S to G. And then we have a and then we will obtain an isomorphism on equalizers. This isomorphism will be induced by inclusion. S from S to this representable functor. Okay, thus we have isomorphism, but we know that if we have this isomorphism, it means that E E is a sheaf. E is a sheaf, and we've proved this proposition. Okay. Now I want to prove that we can think about the set of open spaces on topological space X as a partially ordered sets. It's just I'll write now what I mean. Proposition for any space X, there is an isomorphism between open sets on X and subsheaves of terminal sheaf. Terminal sheaf is just home to X, and thus the topology of the space X is uniquely characterized by the subsheaves of constant sheaf or terminal sheaf. Okay, and let's prove this. It's quite easy. Given any open set W of X, the W is an open set of X. Then we want to define a functor. Define functor S W, and this functor, and if we take this functor S W of U, where U some V is some open subset of W. Then we will obtain that we say that SW of V equals 1 if V is a subset of W, and otherwise we said that it equals empty. It is equal to empty set. Okay, this factor is a sheaf. So it defines subsheaf of terminal sheaf. It is a sheaf, and it is also subsheaf of the terminal sheaf. Conversely, let S be a subsheaf of the terminal sheaf. Then S of U equals 1 or empty set, and also if we have if we have that S of U equals 1 and V is a subset of U, then S of V is equal to 1 also, because as a restriction. And then we can set following. We can form the following set, which consists of all such U in O of X, such that SU is equal to 1 point set. And it's easy to see that for all open sets U, SU equals 1 point set if and only if U is a subset of W, that is S equals SW. Okay. It was an easy proposition. And the conclusion of this topic. The category of sheaves of sets on a space X determines the topology of X. As we have the following projection. Okay. And now I want to discuss I want to discuss germs and an interesting statement which says that every sheaf on X can be regarded as a sheaf of cross section of some bundle, but okay, cross sections of bundles and sheaves. First of all, I recall that for the bundle P from Y to X, this is just a continuous map. We can define the sheaf. Sheaf gamma for this bundle, and it will be a functor and it is called the sheaf of cross sections of the bundle. Sheaf of cross sections of the bundle P. And it, of course, it comes from algebraic topology, algebraic geometry also. It is an important object in mathematics. Okay, and our aim is to prove that every sheaf on X can be regarded as a sheaf of cross sections of some bundle. Okay, and now I want to discuss such objects as a germs. Example. This example comes from complex analysis. We can consider holomorphic functions in a domain in complex plane, and two holomorphic functions are if they are equal in some neighborhood. If we have functions f and g, and if f restricted to v equals g, restricted to v, and v is a some open set which is not empty over U, then we have that f and g are equal in entire open set U. And it is not true for example, real valued functions. but this example is important. And in general setting, we say that functions f and g have the same germ at a point, some point x, if they agree in some open neighborhood of point x, in some open neighborhood of x, and thus we have an equality of germs. It follows that the values in this point are equals for these functions, but converse statement is not true in general case. Okay, and consider any press sheaf. Consider any press sheaf. P and also point x, and open sets v, u, and v are neighborhoods of x, and also consider functions s from pu and c from pv. Then we can give the following definition. Elements S and T have the same germ at X, when there exists open set W, which is a subset over intersection over U and V, with X belongs to W, and S restricted to W equals T restricted to W, belongs to PW. And in this setting, we will say that these functions have the same germ at X, and it is also an equivalence relation, and classes of this equivalence relation are called the germs of X of S at point X. Germ S at point X is the equivalence class. of any S and equivalence like this. This is a equivalence relation. Okay. Denote by means of px. Px is a set of all germs at the point x for all s in Pu, where U is a open set such that U x belongs to U. Okay. This is a set of all germs at x. And it is called the stock at x. Okay, obviously we have that px is the same as a colimit of Pu if we take different U and take the colimits over Pu, then we will obtain obviously Px. Px is the same as a stock at x. Okay. And now we can notice the following fact. That if we have a morphism between press sheaves P and Q, that is it is just a natural transformation between these functors. Then it induces at each point x a unique functor hx from the stocks from between the stocks from px to qx, and such that the following diagram commutes. Oh. And the vertical arrows is just taking germs at the point x, and it follows thus. It follows that the assignments P to Px for object, and for morphisms, the following map H to HX for morphisms is a functor. Is a functor from the praise sheaves to the sets. And it is just take the germ at X. Okay, and now we want to define the following important bundle. But first of all, we should define the set lambda p is a union of all stocks. Just all stocks. All stocks. Germ SX, or where X goes to X and S goes to PU. And there is an obvious bundle P from lambda P to X, and we should take germ S at X, and P of this one is just X. Ooh. Just X. And also we have a section.
What is the topology on lambda?
That's a good question. Okay. The topology of lambda P. We say that the following sets form a basis of topology. S dotted is just following the map from open U to lambda P, such that S dotted of X equals germ S at X. And we say that these sets are basis form the basis of the topology over lambda P. Okay, and this map is just a section of this bundle, and in this topology, in this topology, P and S dotted are continuous. This is an exercise. Okay. Moreover, the bundle P from lambda P to X is local homeomorphism. Is local homeomorphism, and more precisely, it means that each point germ as at X has the open neighborhood as dotted over U, and P restricted to this open neighborhood has the map as a two-sided inverse. Okay. And also we can notice that lambda P is usually not Hausdorff. And the example of this situation, we can illustrate this by means of this example. Let P is a sheaf of continuous real valued functions. Functions on R, and we can take f equals x squared, where when x is a positive or equals 0, or 0 if x is negative. And the function g equals 0 for all x in R, and then we can find that these functions we can find then that germ f at the point 0 is not equal to germ OG in 0, but obviously germ f x equals germ gx for all x, for all negative x, and thus any neighborhoods of f, any neighborhood of f intersects every neighborhood of germ g at 0. Intersects if we take germ f at 0, then any neighborhood will intersect will it intersect neighborhood of germ G in 0, intersects any neighborhood of germ G at 0. Okay, and now define the following important function. Consider for a given press sheaf, P is a press sheaf. And for this press sheaf, we can form the sheaf gamma lambda P, which consists of all sections of the bundle. And there is a function at eta u from between. There is a natural transformation between factor of inclusion I to the factor gamma lambda P, gamma lambda, and such that for any P we have for any sorry. For any P and for any U, we have that eta U of the function S equals a germ germ of S. Germ of S as dotted is the following function, which associate for each X the germ of S at the point X, and here we can form this map, and eta U of S is just S dotted, and S dotted belongs to the section. It is just a section of this bundle over U. Oh, sorry. Okay. And eta is actually a natural transformation, and theorem if the press sheaf if the press sheaf is sheaf, if the press sheaf P is a sheaf, then eta is an isomorphism. And we have the following isomorphism. Okay. Let's prove this theorem. It is not hard. The first point is that eta u is an injection. Oh, sorry. What's happened? Okay, thank you. Eta u is an injection. Okay. Assume that S dotted equals T dotted, and then we should prove that S and T are equals for ST from PU. Okay. This equality means that germ S at X equals germ T at X for all X in U. And this means that there exists open neighborhood of the point X in U such that S restricted to Vx equals C restricted to Vx. And we can form an open open cover form the open cover U, which consists of the elements Vx. U is equal to the union of Vx, and thus S and T have the same image in the corresponding equalizer. But by means of the corresponding condition in the definition of sheaves, it means that S equals T as there exists at most one such a function. Okay, it proves the injectivity. And the second point is eta u is a surjection. Okay, we divide the proof into some steps. The first one, let H from U to lambda be any cross section of the bundle. bundle of germs over over some open set U. The second step, then for any x in U, there exists an open neighborhood Ux, and the function Sx in Pux such that h of x equals germ Sx at the point x, where x in Ux. Okay. The next step, h is continuous. And h is continuous, of course. And the set S dotted over Ux, which is a subset over lambda p, is open by definition of the topology. Then there exists an open neighborhood of X, which is a subset of Ux, such that h of Vx is a subset of Sx dotted of Ux by definition of a continuous function. Hence, we have that h equals Sx dotted on Vx. The next step, we have a covering of the covering of U by open sets Vx for each x, and Sx restricted to Vx we have a covering, and for each open set Vx, we have the following function. Thus, we can write that Sx dotted restricted to the intersection of Vx and Vy equals h, because we have the following quality in this step. And then we have this equality, and also it equals Sy dotted restricted to Vx intersects Vy. And hence we can conclude that germ Sx at the point z equals germ Sy at point z, and hence Sx restricted to the intersection, and Sy is the same. It follows from injectivity. Okay, and the last step, thus, The family of elements, Sx has the same image in equalizer PVX to PVX intersects VY. And by means of definition of sheaves, we have that this family of sets is uniquely collectible, and hence there exists unique S in PU with the property that S restricted to Vx equals Sx. And hallelujah, then at each x, we have that h of x equals germ Sx at point x, which is the same as a germ S at x, and h is equal to S dotted. Okay. And now I have 10 minutes. Yes, it is. T 10 minutes?
Yeah, probably.
Perhaps I'll formulate the theorem. Okay. The next theorem. It turns out that eta is a unit of the adjunction, and this states the following theorem for any press sheaf P morphism eta from P to gamma lambda E of press sheaves is universal. That is, we have the following diagram for any morphism. Theta from P to F, where F is a sheaf, we have the following diagram. P to F factors through the eta. And there exists a unique map sigma, such that the following diagram computes. Okay. And perhaps I can prove the first point. It is quite easy and simple. I think I can prove this. Proof of the factorization. Of the factorization property. We know that eta is an isomorphism. Hence, we can construct the map in converse direction, and we can form the following diagram. We have a natural transformation theta here, and we have an isomorphism eta here. And here we can, here we have an isomorphism gamma lambda f. And here we have a natural transformation like this. And then there exists the map sigma such that this triangle commutes. It's easy to see how it can be constructed. We should we just take
why the map from P to gamma lambda P is an isomorphism? P is just a pre-sheaf. I mean, it's clear.
Okay, thank you. Okay, yes, it is. It's just just a transformation, just a map. Okay, and we have this diagram, and we know that this sort of square commutes, and also and we said that sigma is the following composition: gamma lambda theta and eta reversed. Inversed. Okay, and then we have a we obtain that this triangle commutes and the outer square commutes, and this implies that this triangle also commutes, and it means that we have proved this statement, but also we should prove that the map sigma is unique, and I think I think we can try to do it. The second, the map sigma is unique. Oh, unique. It follows from the following lemma. Let P and be a press sheaf on X, and let sigma and tau natural transformations be two maps. B2 maps into a sheaf. F is a sheaf. sheaf on X, of course. If we have the following equality of the compositions, then we have that sigma and tau is the same. And proof of this lemma the first step, consider a section H from gamma lambda P over U, and for X in U, there exists an open neighborhood of X, and also there exists a function Sx belongs to PVX such that H of X is just a germ Sx at the point X. Okay, then choose these open neighborhoods so small, if needed, that the following holds: H restricted to Vx equals Sx dotted equals eta Vx of S. But this is by definition of eta. And okay, the next step, thus sigma of H restricted to Vx equals sigma of H restricted to Vx. This is by definitions, and equals sigma over eta, sigma eta of Sx, and this by definition of eta equals we have this composition, and we can replace this composition by this one, tau eta of Sx, and in the same way equals tau H restricted to Vx equals tau of H restricted to Vx, and thus the next step, but the set of the sets Vx where x belongs to U is a cover covering of U, and F is a sheaf, of course. And by definition of sheaf, it implies that sigma of H, we have the following quality, and by definition of sheaf, we have that sigma of H equals tau of H for all H from lambda P, and thus sigma and tau are the same. Okay. now we have proved the following theorem, and well, I think I can formulate an important corollary, a very important corollary, which tells us that for any topological space X, the category of sheaves on X is reflective. It means that reflective in the category of press sheaves. It means that the inclusion factor sheaves into press sheaves has a left adjoint. And the easy proof this is just a theorem, the second theorem. The second theorem asserts that the composition is a left adjoint to the inclusion factor I. I recall that we have the map eta from I to the composition. Okay, and eta is a unit. Eta is a unit of the is the unit of the adjunction. And this corollary gives us another way to prove that to prove the previous statement. What is the statement? Just a second. This proposition that any topological space, the category of sheaves has all limits and inclusion no, it is not. It isn't so. Yes, it isn't so. Because if we have co-limits, that it's okay. But this in this setting we have limits and left adjoint. Left adjoint preserves co-limits. Yes.
Yeah, I think yes.
Okay. But anyway, this theorem is important, and I think we can stop at this point. Have you any questions? Okay, then we can stop recording. The recording. Okay.